This video is on the reactions of complex ions. We're not going to look at all the reactions of complex ions in this video, but we are going to look at how to write equations for ligand substitution reactions, explain why the substitution of a unidentate ligand with a bidentate or multidentate ligand leads to a more stable complex, and write equations for the redox reactions of complex ions. So I'm not going to show you all the ligand substitution reactions you need to know for your exam, but I am going to show you one just to show you the pitfalls that there are when writing these. So I'm going to take the copper hexaquar ion, (2+), and I'm going to react that with HCl. Now, when it's reacting with hydrochloric acid, it's not actually the hydrogen that does anything, it's just the chloride ions. So we can just write the chloride ions in, and this forms CuCl4. Now, this is the main thing that people get wrong when they're writing ligand substitution reactions, and that is the charge on the new product. Because it's very easy just to take this across and assume it's 2+ again, but actually you've got to realise that you're adding a negative thing to the 2+ ion. And so the overall charge on this will be the sum of the charge on the copper and the charges on the 4 chloride ions. So that's going to be 2+, take away 4 from the 4 chloride ions. So the new charge is going to be 2-. So you must make sure you just check what the new charge is going to be and just think about it before just writing. And you're also going to make 6H2O because they've been chucked off, and you're going to need 4 chloride ions in order to complete that. So the key is, with writing ligand substitution reactions, to know what your product is first, and you can do that by learning the table I gave you, and also just checking what the charge is on the new product by thinking about the charges on the ligands and the charges on the central metal ion. So this next time I want you to consider this following reaction. So you've got the Edta ligand, which comes up in a different one of my videos. So that is a multidentate ligand. It can form 6 dative bonds with the central metal ion, reacting with the hexaquar copper complex to form CuEdTA, and that's going to be 2- in the end because EdTA is 4-, and 6 waters. Now this is a much more stable compound than this, and we can describe why based on the chelate effect. And this is based on the whole idea of entropy change. So an increase in entropy is seen as being favourable. And basically entropy is the measure of disorder in a system. So you can see that we go from 2 molecules on the left-hand side here, or ions if you like, sorry, 2 ions on the left-hand side here, to make 7 ions on the other side. So there's an increase in entropy, and that's what makes this reaction favourable, and also what makes this compound more stable than this one. If you were to describe why this is favourable, or why this compound is more stable, you would say that there are 2 species on the left and 7 species on the right. Therefore, there is an increase in disorder, so an increase in entropy. And remember, when entropy increases, that is favourable. So I have covered this next aim in a different video, but I'm going to cover it again in this one just because it's quite a tricky concept, so there's no harm in doing it twice. And I'm going to take an example of cobalt with 6 ammonias around it, 2+, being oxidised to cobalt 3+, by hydrogen peroxide. So essentially all you do here is exactly the same as you would do for other redox reactions. You need to balance everything with charges and combine 2 half equations. So here we're just going to add an electron to balance the charges, everything else is balanced, and we're using hydrogen peroxide to do this. So your hydrogen peroxide is going to form something. Now, at the moment, it's not obvious what that is, but we do know it's an alkaline solution, because to get cobalt with 6 ammonias around it, we have to add excess ammonia, which is an alkali. So, what we can do is balance this first with the normal way. So we'll do that. So we need to balance the oxygens by adding water, then balance hydrogens by adding H+, then balance electrons. But then we'll find that we've now got this in acidic solution. So instead we're going to convert this back into alkaline solution by adding OH- to get rid of the H+. So we add 2H- on both sides. And then what you'll find is this will form 2 waters, which will cancel out the 2 waters here, and then we've got H2O2 forming 2OH-, so that's in alkaline conditions. We then multiply the top one up by 2 to make the electrons balance, and so the overall redox reaction is CO2CO NH36, 2 plus H2O2 goes to make 2CO NH36, 3 plus 2OH-. So, simple as that. All you need to do is just make sure that you balance the 2 half equations. If it's in alkaline conditions, make sure you don't have any H pluses by adding OH- on both sides, and then combine them. So let's have a look at a couple of past exam questions on this. So the complex cisplatin acts as an anti-cancer drug by changing the properties of DNA when it reacts with guanine, a component of DNA. When cisplatin is absorbed into the human body, it undergoes a ligand substitution reaction, and one chloride ligand is replaced by a water molecule forming a complex ion Q. Write an equation for this substitution reaction to form the complex ion Q. So you've got your cisplatin, which is PT NH3 2Cl2. That has no charge. And then we're adding water, and that's kicking off one of your chloride ions. So you're going to make PT NH3 2 H2O Cl. And this is now going to have a charge, because now you've only got one negatively charged chloride ion, and before you had 2. So this is now going to have a +1 charge, and you're also going to have kicked out a Cl-. So that is the pitfall that I described earlier. Just make sure you think about that when you're drawing your product. Next question. The ligand EDTA is shown below. Draw circles around the atoms of 2 different elements that link to a transition metal ion by a coordinate bond on EDTA4- pairs ligand. Now I haven't really covered that in this video, but I have covered it in a different video, so if you watched that, you would know that it is these negatively charged oxygens and the nitrogen, which form dated bonds with a central metal ion. And then we have write an equation for the reaction between EDTA4- and COH2O 6,2+ ion. Use the abbreviation EDTA4- in your equation. So we have COH2O 6 2+ plus EDTA4-. Remember, it's a multidentate ligand, forms 6 bonds with the cobalt, so that is just going to knock out all 6 waters. And the overall charge on this is now going to be 2-, and you also have 6 water molecules. And then explain why the complex ion formed as a product of the reaction is more stable than the CO hexarachor ion. So this is because there is an increase in entropy, and that is because there are 2 species on the left and 7 on right. So 2 species form 7 species, and therefore there's an increase in entropy. And finally, write an equation for a reaction that occurs between an aqueous solution of cobalt sulfate and an excess of aqueous diaminoethane. Draw a diagram to show the shape of and bonding in the complex product. Write an equation for the reaction that would occur if the complex product of this reaction were allowed to stand in contact with oxygen gas. So, first we'll write an equation. So you've got cobalt 2 sulfate. So the sulfate ions are not important, it's because it's an aqueous solution, so it's going to form the hexaqua ion. 2 plus. Plus diaminoethane, so that is your H2N, CH2, CH2, NH2. And because this is a 2 plus ion, it's going to do ligand substitution. So what you're going to make is cobalt, and then NH2, CH2, CH2, NH2, and this is a bidentate ligand, so you're going to fit 3 of these around the cobalt. Still going to be 2 plus because it's neutral, the diaminoethane, and you're going to form 6 waters as well because they've been knocked off. And then draw down and show the shape of and bonding in the complex product. So you got cobalt, and it's octahedral. Now when you're drawing these, make sure you draw the bonds first, then draw the ends, which are forming the dated bonds, and then connect up pairs of ends with your carbons, and then add the hydrogens, so NH2, CH2, CH2. Like so, and that has a 2 plus charge. And then it says, write an equation for the reaction that would occur if the complex product of this reaction were allowed to stand in contact with oxygen gas. I'm just going to zoom out a little bit so I have some space. So, if this was allowed to stand in oxygen, then the 2 plus would turn to 3 plus. So what you're going to get is CO, NH2, CH2, CH2, NH2, 3, 2 plus, turning into the same but with the 3 plus charge. And you need an electron on the right hand side to balance that. And then it's standing in oxygen gas, you've got O2 turning into, we don't know at the moment. So we're going to balance this, so we're going to make 2 waters, and we're going to have 4H plus 4 electrons, and then we need to multiply the top one up by 4 for the electrons to cancel, and then if we add them together we've got 4 CO, NH2, CH2, CH2, NH2, 3, 2 plus 4H plus O2 goes to make 4 CO, NH2, CH2, CH2, NH2, 3 plus 2 H2O. The reason why I didn't have to convert this into a different form like I have done before is because it didn't specify that it was an alkaline solution, so it's fine to leave it in acidic solution in this case.